All right, happy Friday, everyone. Um, as a heads up, we're going to spend just a couple minutes on the last slide in Module 3, and then I'm going to switch over to the slide set for Module 4, which I think I uploaded a couple of hours ago. So be ready for that. Any questions before we launch into what I want to talk about? Okay. So I think that this is an appropriate time to introduce this kind of graph, which is kind of rife. It's all throughout digital communications. And I want to kind of walk you through. It's not so important how this is generated, but really it's more important that you could interpret it. I'd like you to be able to generate one for yourself eventually. But let's just think about what's going on here. So I've heard this called a waterfall plot. I've also heard other things called waterfall plots, so it might not be the best name to give it. But the big picture is that we are looking at bit energy per noise power. And so, I mean, you could think of noise energy as being the power within one bit period. So if taking this ratio with different units is bothering you, you can always convert from one to the other because we're talking about a fixed bit period here. And then they're also looking at this in decibels. So this is, for all intents and purposes, this is a signal-to-noise ratio on the horizontal. And on the vertical, we are, well, in this particular plot, it's telling us the probability of symbol error. So this is probability of error. And in this particular plot, it's for symbols, but in other plots, you'll see this is the probability of a bit error, also known as the bit error rate. So this particular plot, because it's supposed to be for MPAM, so multi-level pulse amplitude modulation, they are just reporting the error in symbol decoding, and each symbol would then contain log m bits, so you would then get a different number of bit errors depending on which symbol itself was actually incorrectly decoded. So, and then it's a little bit not obvious, but this is also on a log scale, right? So here's 10 to the minus 1, 10 to the minus 2. So this is a log-log plot, if we're being honest. Okay, so what the heck's going on here? What are these curves supposed to represent? Well, remember that we want to design our receiver. We want our receiver to make as few errors as possible. Another way to say that is we want the bit error rate to be low. Now, the bit error rate is going to change with SNR, right? If you are sending through a very quiet channel, then we expect your bit error rate to be small. So a quiet channel is a strong SNR, so that pushes us up to the right, and all of these plots fall down, which is good at high SNRs. Now, if you're trying to push data through a noisy channel, then all of a sudden you're living over here on the left. And so that let's pick an SNR where we get actually a couple crossings. So if we have a channel that we've measured and we're pretty consistently getting an SNR of 6 dBs, it's pretty good. Then what I would do as an engineer, I would look up and I would see, okay, at a 6 dB channel condition, if I use 2 PAM, so plus pulse minus pulse, then I can expect, well, we got about 2 times 10 to the minus 3, so 2, what is that, 2 milli errors, or 1 error out of every 500 bits. I think that's the right, on average, that's the right number of bit errors to expect. If I use 4 PAM, so that is, so 4 PAM just means 1, 1 gets mapped to maybe 3p. 1, 0 gets mapped to p of t. 0, 1 gets mapped to minus p of t. And 0, 0 gets mapped to negative 3p of t. So this is still pulse amplitude modulation. What we're doing is we're mapping the bits to the amplitudes of these pulses. And it also means that we're kind of just living in one dimension on the IQ diagram. Okay, so if I go to 4PAM, then my bit error rate jumps for the same SNR. Now I'm expecting, what, 0.05. So this is 1 bit in every 20 is going to be flipped. Or sorry, 1 symbol in every 20 is going to be flipped. Does that make sense? If I increase the number of levels in my symbols, that my bit error rate gets worse? Can anyone justify that?
Well, it kind of reminds me of the Quam problem in some sense. They have like closer thresholds. So when you get a certain point that there are more options now that the bit could go to.
Sure, absolutely. So back with just 2PAM, if we had noise that landed anywhere on the right half plane, we were correct. But now in 4PAM, the Voronoi regions, if we've got, here's P of t, here's 3P of t, the Voronoi regions are now these little strips. And now all of a sudden, if we transmitted this guy, then we have more opportunity for error, right? So before, if we received this noise vector, or this received vector, in this situation, it would be a correct decoding. But in this situation, we'd get an error. Okay, so the denser your constellation, and this counts as more dense, right, because there's more points. The denser your constellation, the more susceptible to a given noise level your system will be. I hope that makes sense. Okay, so that would be kind of your channel is fixed, it's known, it's not time varying. That would be, and then this would allow you to say, okay, if I needed a good bit error performance, I would probably have to use the less dense constellation. Okay, if I had super robust error correction, then I would probably go for this one and say, okay, I can handle 1 bit in 20 being flipped because I can correct for that. The trade-off with using m equals 4 is that I double my bit rate for any given point in time. All right. So the other, I think that's a more common way to interpret these diagrams is actually going on the vertical and then looking down, if you will. So this is something like, I have a maximum allowable bit error rate. Let's say at most, I can tolerate 1 in 1,000 bits being flipped because I couldn't afford a good error correction code, and if anything more than this, my audio becomes jumpy and no one can understand me, or something like that. Whatever the requirements come from. Then you would then, of course, look across here and say, okay, if I use 2PAM, then I would be able to transmit in a 6.5 dB SNR situation. But if I went up to 8PAM, that would mean that my channel condition would have to be 16 dBs in order to achieve the same bit error rate. So in this sense, you could use maybe a feedback mechanism to say, well, let's try and load 4 bits per symbol as for when the channel is good, right? For when we're seeing channel conditions of 16 dBs of SNR. But then maybe we get some feedback in the loop and we are measuring our channel situation diminishing, so our SNR shrinks. Then maybe we'd have to be more modest with our encoding techniques. Okay. So these are pretty powerful diagrams, and I just wanted to call your attention to the fact that they can be read either from horizontal to vertical or from vertical back to horizontal. All right. Any questions there? When I first saw them, the fact that bad things are on top and good things are at the bottom, that for some reason I had a hard time wrapping my mind around that. I don't know. Maybe it's just me.